Magnesium. Magnesium is a chemical element with symbol Mg and atomic number 12. It is a shiny gray solid which bears a close physical resemblance to the other 5 elements in the second column of the periodic table. All group 2 elements have the same electron configuration in the outer electron shell and a similar crystal structure. Magnesium is the 9th most abundant element in the universe. It is produced in large, aging stars from the sequential addition of 3 helium nuclei to a carbon nucleus. When such stars explode as supernovas, much of the magnesium is expelled into the interstellar medium where it may recycle into new star systems. Magnesium is the 8th most abundant element in the Earth's crust and the 4th most common element in the Earth, making up 13% of the planet's mass and a large fraction of the planet's mantle. It is the 3rd most abundant element dissolved in seawater, after sodium and chlorine. Magnesium occurs naturally only in combination with other elements, where it invariably has a +2 oxidation state. The free element can be produced artificially, and is highly reactive. The free metal burns with a characteristic brilliant white light. The metal is now obtained mainly by electrolysis of magnesium salts obtained from brine, and is used primarily as a component in aluminium-magnesium alloys, sometimes called magnesium or magnesium. Magnesium is less dense than aluminium, and the alloy is prized for its combination of lightness and strength. Magnesium is the 11th most abundant element by mass in the human body and is essential to all cells and some 300 enzymes. Magnesium ions interact with polyphosphate compounds such as ADP, DNA, and RNA. Hundreds of enzymes require magnesium ions to function. Magnesium compounds are used medicinally as common laxatives, antacids, and to stabilize abnormal nerve excitation or blood vessel spasm in such conditions as eclampsia. Elemental magnesium is a gray-white lightweight metal, 2/3 the density of aluminium. It tarnishes slightly when exposed to air, although, unlike the heavier alkaline earth metals, an oxygen-free environment is unnecessary for storage because magnesium is protected by a thin layer of oxide that is fairly impermeable and difficult to remove. Magnesium has the lowest melting, and the lowest boiling point 1363 K of all the alkaline earth metals. Magnesium reacts with water at room temperature, though it reacts much more slowly than calcium, a similar group 2 metal. When submerged in water, hydrogen bubbles form slowly on the surface of the metal though, if powdered, it reacts much more rapidly. The reaction occurs faster with higher temperatures. Magnesium's reversible reaction with water can be harnessed to store energy and run a magnesium-based engine. Magnesium also reacts exothermically with most acids such as hydrochloric acid, producing the metal chloride and hydrogen gas, similar to the HCl reaction with aluminium, zinc, and many other metals. Magnesium is highly flammable, especially when powdered or shaved into thin strips, though it is difficult to ignite in mass or bulk. Flame temperatures of magnesium and magnesium alloys can reach 3100 degrees C, although flame height above the burning metal is usually less than 300 mm. Once ignited, such fires are difficult to extinguish, because combustion continues in nitrogen, carbon dioxide, and water. This property was used in incendiary weapons during the firebombing of cities in World War II, where the only practical civil defense was to smother a burning flare under dry sand to exclude atmosphere from the combustion. Magnesium may also be used as an igniter for thermite, a mixture of aluminium and iron oxide powder that ignites only at a very high temperature. Organomagnesium compounds are widespread in organic chemistry. They are commonly found as Grignard reagents. Magnesium can react with haloalkanes to give Grignard reagents. Examples of Grignard reagents are phenyl magnesium bromide and ethyl magnesium bromide. The Grignard reagents can function as a common nucleophile, attacking the electrophilic group such as the carbon atom that is present within the polar bond of a carbonyl group. Relevant organic magnesium reagents outside the scope of Grignards are magnesium anthracene with magnesium forming a 1,4 bridge over the central hexagon used as a source of highly active magnesium, and butadiene magnesium and a duct with butadiene and a source for the butadiene dianion. When burning in air, magnesium produces a brilliant white light that includes strong ultraviolet wavelengths. Magnesium powder was used for subject illumination in the early days of photography. Later, magnesium filament was used in electrically ignited single-use photography flashbulbs. Magnesium powder is used in fireworks and marine flares where a brilliant white light is required. It was also used for various theatrical effects, such as lightning, pistol flashes, and supernatural appearances. Magnesium is the 8th most abundant element in the Earth's crust by mass and tied in 7th place with iron in molarity. It is found in large deposits of magnesite, dolomite, and other minerals, and in mineral waters, where magnesium ion is soluble. Although magnesium is found in more than 60 minerals, only dolomite, magnesite, brucite, carnallite, talc, and olivine are of commercial importance. The Mg2+ cation is the second most abundant cation in seawater, which makes seawater and sea salt attractive commercial sources for Mg. To extract the magnesium, calcium hydroxide is added to seawater to form magnesium hydroxide precipitate. Magnesium hydroxide is insoluble in water and can be filtered out and reacted with hydrochloric acid to produce concentrated magnesium chloride. From magnesium chloride, electrolysis produces magnesium. As of 2013, magnesium alloy consumption was less than 1 million tons per year, compared with 50 million tons of aluminum alloys. Its use has been historically limited by its tendency to corrode, creep at high temperatures, and combust. The presence of iron, nickel, copper, and cobalt strongly activates corrosion. Greater than a very small percentage, these metals precipitate as intermetallic compounds, and the precipitate locales function as active cathodic sites that reduce water, causing the loss of magnesium. Controlling the quantity of these metals improves corrosion resistance. Sufficient manganese overcomes the corrosive effects of iron. This requires precise control over composition, increasing costs. Adding a cathodic poison captures atomic hydrogen within the structure of a metal. This prevents the formation of free hydrogen gas, an essential factor of corrosive chemical processes. The addition of about 1 in 300 parts arsenic reduces its corrosion rate in a salt solution by a factor of nearly 10. Research showed that magnesium's tendency to creep at high temperatures is eliminated by the addition of scandium and gadolinium. Flammability is greatly reduced by a small amount of calcium in the alloy. Magnesium forms a variety of compounds important to industry and biology, including magnesium carbonate, magnesium chloride, magnesium citrate, magnesium hydroxide, magnesium oxide, magnesium sulfate, and magnesium sulfate heptahydrate. Magnesium has 3 stable isotopes, 24 mg, 25 mg, and 26 mg. All are present in significant amounts. About 79% of Mg is 24 mg. The isotope 28 mg is radioactive and in the 1950s to 1970s was produced by several nuclear power plants for use in scientific experiments. This isotope has a relatively short half-life and its use was limited by shipping times. The nuclide 26 mg has found application in isotopic geology, similar to that of aluminium. 26 mg is a radiogenic daughter product of 26Al, which has a half-life of 717,000 years. Excessive quantities of stable 26 mg have been observed in the Cal-rich inclusions of some carbonaceous chondrite meteorites. This anomalous abundance is attributed to the decay of its parent 26Al in the inclusions, and researchers conclude that such meteorites were formed in the solar nebula before the 26Al had decayed. These are among the oldest objects in the Solar System and contain preserved information about its early history. It is conventional to plot 26 mg/24 mg against an Al/mg ratio. In an isochron dating plot, the Al/mg ratio plotted is 27 Al/24 mg. The slope of the isochron has no age significance, but indicates the initial 26 Al/27 Al ratio in the sample at the time when the systems were separated from a common reservoir. China is the dominant supplier of magnesium, with approximately 80% of the world market share. China is almost completely reliant on the silicothermic pigeon process to obtain the metal. The process can also be carried out with carbon at approximate 2300 degrees C. In the United States, magnesium is obtained principally with the Dow process, by electrolysis of fused magnesium chloride from brine and seawater. A saline solution containing Mg2+ ions is first treated with lime and the precipitated magnesium hydroxide is collected. The hydroxide is then converted to a partial hydrate of magnesium chloride by treating the hydroxide with hydrochloric acid and heating of the product. The salt is then electrolyzed in the molten state. At the cathode, the Mg2+ ion is reduced by 2 electrons to magnesium metal. At the anode, each pair of Cl ions is oxidized to chlorine gas, releasing 2 electrons to complete the circuit. A new process, solid oxide membrane technology, involves the electrolytic reduction of MgO. At the cathode, Mg2+ ion is reduced by 2 electrons to magnesium metal. The electrolyte is yttria-stabilized zirconia. The anode is a liquid metal. At the YSZ/liquid metal anode, O2 is oxidized. A layer of graphite borders the liquid metal anode, and at this interface carbon and oxygen react to form carbon monoxide. When silver is used as the liquid metal anode, there is no reductant carbon or hydrogen needed, and only oxygen gas is evolved at the anode. It has been reported that this method provides a 40% reduction in cost per pound over the electrolytic reduction method. This method is more environmentally sound than others because there is much less carbon dioxide emitted. The United States has traditionally been the major world supplier of this metal, supplying 45% of world production even as recently as 1995. Today, the U.S. market share is at 7%, with a single domestic producer left, U.S. Magnesium, a Renco Group company in Utah born from now-defunct MagCorp. The name magnesium originates from the Greek word for a district in Thessaly called Magnesia. It is related to magnetite and manganese, which also originated from this area, and required differentiation as separate substances. See manganese for this history. In 1618, a farmer at Epsom in England attempted to give his cows water from a well there. The cows refused to drink because of the water's bitter taste, but the farmer noticed that the water seemed to heal scratches and rashes. The substance became known as Epsom salts and its fame spread. It was eventually recognized as hydrated magnesium sulfate, MgSO47H2O. The metal itself was first isolated by Sir Humphry Davy in England in 1808. He used electrolysis on a mixture of magnesia and mercuric oxide. Antoine Bussy prepared it in coherent form in 1831. Davy's first suggestion for a name was magnium, but the name magnesium is now used. Magnesium is the third most commonly used structural metal, following iron and aluminium. The main applications of magnesium are, in order, aluminium alloys, die casting, removing sulfur in the production of iron and steel, and the production of titanium in the Kroll process. Magnesium is used in super-strong, lightweight materials and alloys. For example, when infused with silicon carbide nanoparticles, it has extremely high specific strength. Historically, magnesium was one of the main aerospace construction metals and was used for German military aircraft as early as World War I and extensively for German aircraft in World War II. The Germans coined the name electron for magnesium alloy, a term which is still used today. In the commercial aerospace industry, magnesium was generally restricted to engine-related components, due to fire and corrosion hazards. Currently, magnesium alloy use in aerospace is increasing, driven by the importance of fuel economy. Development and testing of new magnesium alloys continues, notably Electron 21, which has proved suitable for aerospace engine, internal, and airframe components. The European Community runs 3 R&D magnesium projects in the Aerospace Priority of 6 framework program. In the form of thin ribbons, magnesium is used to purify solvents, for example, preparing super-dry ethanol. Both AJ62A and AE44 are recent developments in high-temperature low-creep magnesium alloys. The general strategy for such alloys is to form intermetallic precipitates at the grain boundaries, for example by adding misc metal or calcium. New alloy development and lower costs that make magnesium competitive with aluminium will increase the number of automotive applications. Because of low weight and good mechanical and electrical properties, magnesium is widely used for manufacturing of mobile phones, laptop and tablet computers, cameras, and other electronic components. Magnesium, being readily available and relatively non-toxic, has a variety of uses. Magnesium metal and its alloys can be explosive hazards. They are highly flammable in their pure form when molten or in powder or ribbon form. Burning or molten magnesium reacts violently with water. When working with powdered magnesium, safety glasses with eye protection and UV filters are employed because burning magnesium produces ultraviolet light that can permanently damage the retina of a human eye. Magnesium is capable of reducing water and releasing highly flammable hydrogen gas. Therefore, water cannot extinguish magnesium fires. The hydrogen gas produced intensifies the fire. Dry sand is an effective smothering agent, but only on relatively level and flat surfaces. Magnesium reacts with carbon dioxide exothermically to form magnesium oxide and carbon. Hence, carbon dioxide fuels rather than extinguishes magnesium fires. Burning magnesium can be quenched by using a Class D dry chemical fire extinguisher, or by covering the fire with sand or magnesium foundry flux to remove its air source. Magnesium compounds, primarily magnesium oxide, are used as a refractory material in furnace linings for producing iron, steel, non-ferrous metals, glass, and cement. Magnesium oxide and other magnesium compounds are also used in the agricultural, chemical, and construction industries. Magnesium oxide from calcination is used as an electrical insulator in fire-resistant cables. Magnesium reacted with an alkyl halide gives a Grignard reagent, which is a very useful tool for preparing alcohols. Magnesium salts are included in various foods, fertilizers, and microbe culture media. Magnesium sulfite is used in the manufacture of paper. Magnesium phosphate is used to fireproof wood used in construction. Magnesium hexafluorosilicate is used for moth-proofing textiles. The important interaction between phosphate and magnesium ions makes magnesium essential to the basic nucleic acid chemistry of all cells of all known living organisms. More than 300 enzymes require magnesium ions for their catalytic action, including all enzymes using or synthesizing ADP and those that use other nucleotides to synthesize DNA and RNA. The ADP molecule is normally found in a chelate with a magnesium ion. Spices, nuts, cereals, cocoa, and vegetables are rich sources of magnesium. Green leafy vegetables such as spinach are also rich in magnesium. In the UK, the recommended daily values for magnesium are 300 mg for men and 270 mg for women. In the US, the recommended dietary allowances are 400 mg for men ages 19-30 and 420 mg for older, for women 310 mg for ages 19-30 and 320 mg for older. Numerous pharmaceutical preparations of magnesium and dietary supplements are available. In 2 human trials, magnesium oxide, one of the most common forms in magnesium dietary supplements because of its high magnesium content per weight, was less bioavailable than magnesium citrate, chloride, lactate, or aspartate. An adult has 20–26 grams of magnesium, with 60% in the skeleton, 39% intracellular, and 1% extracellular. Serum levels are typically 0.71.0 mol/L or 1.82.4 milliequivalent/L. Serum magnesium levels may be normal even when intracellular magnesium is deficient. The mechanisms for maintaining the magnesium level in the serum are varying gastrointestinal absorption and renal excretion. Intracellular magnesium is correlated with intracellular potassium. Increased magnesium lowers calcium and can either prevent hypercalcemia or cause hypocalcemia depending on the initial level. Both low and high protein intake conditions inhibit magnesium absorption, as does the amount of phosphate, phytate, and fat in the gut. Unabsorbed dietary magnesium is excreted in feces, absorbed magnesium is excreted in urine and sweat. Magnesium status may be assessed by measuring serum and erythrocyte magnesium concentrations coupled with urinary and fecal magnesium content, but intravenous magnesium loading tests are more accurate and practical. A retention of 20% or more of the injected amount indicates deficiency. No biomarker has been established for magnesium. Magnesium concentrations in plasma or serum may be monitored for efficacy and safety in those receiving the drug therapeutically, to confirm the diagnosis in potential poisoning victims, or to assist in the forensic investigation in a case of fatal overdose. The newborn children of mothers who received parenteral magnesium sulfate during labor may exhibit toxicity with normal serum magnesium levels. Low plasma magnesium is common. It is found in 2.5–15% of the general population. From 2005 to 2006, 48% of the United States population consumed less magnesium than recommended in the dietary reference intake. Other causes are increased renal or gastrointestinal loss, an increased intracellular shift, and proton pump inhibitor antacid therapy. Most are asymptomatic, but symptoms referable to neuromuscular, cardiovascular, and metabolic dysfunction may occur. Alcoholism is often associated with magnesium deficiency. Chronically low serum magnesium levels are associated with metabolic syndrome, diabetes mellitus type 2, fasciculation, and hypertension. Sorted by type of magnesium salt, other therapeutic applications include: overdose from dietary sources alone is unlikely because excess magnesium in the blood is promptly filtered by the kidneys, and overdose is more likely in the presence of impaired renal function. In spite of this, megadose therapy has caused death in a young child, and severe hypermagnesemia in a woman and a young girl who had healthy kidneys. The most common symptoms of overdose are nausea, vomiting, and diarrhea. Other symptoms include hypotension, confusion, slowed heart and respiratory rate, deficiencies of other minerals, coma, cardiac arrhythmia, and death from cardiac arrest. Plants require magnesium to synthesize chlorophyll, essential for photosynthesis. Magnesium in the center of the porphyrin ring in chlorophyll functions in a manner similar to the iron in the center of the porphyrin ring in heme. Magnesium deficiency in plants causes late-season yellowing between leaf veins, especially in older leaves, and can be corrected by either applying Epsom salts, or crushed dolomitic limestone, to the soil.